Now let's talk about mapping the solar system, the set of planets. Of course, the three outermost planets in this diagram were not known at this time. The size of the solar system was an important goal for astronomy in the 17th century. By this time, the relative distances to the planets could be determined using Kepler's laws, and the relative sizes of planets could be measured using image sizes with the micrometer technique added to a telescope, but the overall scale remained undetermined. In other words, we needed to measure one absolute or actual size of a planet and one distance from a planet to the Sun to get all the other distances and sizes using Kepler's laws and simple geometry. So the overall scale of the solar system was simply unknown, a long time after the invention of the telescope. The natural unit, as I've said, is the mean distance from the Earth to the Sun. That's abbreviated as the astronomical unit in astronomy. It's a fundamental distance measurement. And it's measured by the solar parallax, the angular distance between the Sun, as measured from the center of the Earth and a point 1 Earth radius away. Or if you wanted the best possible baseline, you would actually have points on opposite sides of the Earth, making the measurement at the same time. Giovanni Domenico Cassini from Bologna constructed a meridian line or sundial in the Basilica of San Pretriono in Bologna. It's a magnificent construction that I visited. He measured the solar diameter and showed how it varied over a year and confirmed to Kepler's second law. He measured the effect of refraction on the Sun's apparent motion, which is an important part of measuring positions, real positions in space as opposed to apparent in the sky. He was the first to measure the obliquity of the ecliptic, which is the tilt of the Earth's spin axis, just under 23.5 degrees. And he attempted a measurement, the first real measurement of the solar parallax, but he didn't get an actual number. He got a limit, finding it to be less than 12 arc seconds. And so we have the early measurements. The pendulum clock, of course, was key to this. Huygens had a pendulum clock with a beautiful regulation of the mechanism and allowing the most precise observation timing available to that point, giving critical motions. The first observations of a planet and distance using the method of parallax and essentially doing trigonometry on this triangle you can see in the diagram with a very small angle was done by Cassini and Richter in the 1670s. So this was based on accurate observations of the position of Mars from two separated locations, Paris and Cayenne, an island in the South Pacific. The observations had to be made at exactly the same time from different places, which is why you needed the accurate clock. Once the distance to Mars is known, the other distances follow. This first estimate was not bad, but it was only accurate to about 10%. We now know the Earth-Sun distance to be 150 million kilometers, or 100 million miles. The size of the planets were determined from known distances, and again, the parent sizes from their micrometers. Meanwhile, another important measurement was made by Romer, a Dutch astronomer, in 1675. He noticed that the eclipses of Jupiter's moons occur slightly later than expected when the Earth is moving away from Jupiter, and slightly early when the Earth is moving towards Jupiter. And these changes are a result of light having to travel further to reach the Earth as the Earth moves in its orbit. You can see from the diagram below. Once again, timing is required to make a measurement of the speed of light with this clever method. Remember, Galileo had tried to measure the speed of light and had not succeeded by flashing lanterns from hillsides separated north of Florence. This was the first measurement of the speed of light with any precision and showed that it was around 300,000 kilometers per second. It's a vital tool of astronomy to know the speed of light, since for the distances of the solar system, light takes hours to travel to us from the outer planets. In 1669, Jean Picard used triangulation to measure meridian arc. This is a distance corresponding to 1 degree of latitude at the same longitude. He obtained 110 and a little bit kilometers for 1 degree, or 6,300 kilometers for the radius of the spherical Earth. So, as you recall, to do this triangulation, you need to know the size of the Earth, the object you're measuring from. And the size of the Earth also was not that well known at the time. So these measurements of the size of the Earth with increased precision were important. They also led to the discovery that the Earth was oblate, that it bulged near the equator. Newton used the result of Picard in his universal law of gravitation. The true size of the solar system came from observations of the transit of Venus. Rickard's discovery that pendulums ran more slowly led to Newton's explanation of the Earth being oblate. And so a program was developed to focus on a very rare set of celestial events. About 8 years apart, separated by over a century, Venus appears to cross the face of the Sun. These are Venus transits. And the Sun as a backdrop gives a perfect way to measure the timing of the transit from two different places on the Earth's surface, and so measure the triangle that gives you the scale of the solar system, the distance to Venus, and then all the other planets. Jeremiah Horrocks observed this transit in 1639 and was the only person to make an actual measurement. His estimate was off by about 30%. And so people redoubled their efforts for the following transit. Remember, they had to wait over a century for the next transit. The two transits were 1761 and 1769. Telescope technology, of course, had improved a lot in this time, and so every astronomer in Europe geared up for observations. It turns out the 1761 transit was observed from 61 different locations, from Canada all the way to China, and the 1769 from even more locations, including, for example, James Cook and Tahiti. Here's what they saw. Edmund Halley actually improved on a suggestion of James Gregory by using the timing of transits and computing the details of the next transits. In this diagram, we see the geometry of observing the transit of Venus. It's done from two different places on the Earth's surface simultaneously using accurate clocks, and the triangle measured gives you the distance to Venus from the Earth, and then by Kepler's law, all the other planet distances, including the distance of the Earth from the Sun, the astronomical unit. This measurement, done with much better precision, with much better telescopes, with much better clocks, thanks to Harrison, determined the Earth-Sun distance with an accuracy of 3%. There were some adventures in this regard. We've seen that James Cook nearly lost his ships to scavenging of nails from the ship to trade for sex with the Tahitians before they could make their measurement. And he risked mutiny from his sailors by getting them off the island in time. Some of these measurements were difficult, some were done better than others, but the result was we know the scale of the solar system. And here's an animation of what the transit of Venus looks like. We have quite a while to wait for the next one. And through this time, we find new members of the solar system. William Herschel, who we'll talk about later, discovers Uranus in 1781, the first new planet to be discovered in human history. Remember, all the other planets are visible to the naked eye. So this is the first new planet discovered in the age of the telescope. Asteroids are also discovered. In 1766, it appears that the radii of planet orbits up to Saturn are described by numerical sequence. We can see in the table below, it's essentially a doubling of the distance with a simple offset. And if you follow this numerical sequence, it looks like there's a gap at 2.8 astronomical units, or 2.8 times the Earth distance from the Sun. And so it's speculated that there should be a planet at this location. This turns out to be the location where not a planet, but a large number of rocks are found, the asteroids. Eventually, when Uranus is found, it fits into this sequence perfectly. And so asteroids are discovered in this time. In 1800, the orbital path for a hypothetical object at 2.8 astronomical units is calculated, and the search is underway. Giovanni Piazza in Italy notices a movement of an 8th magnitude object in the constellation of Taurus in 1801. He observes it and realizes its motion is more planetary than cometary. He notifies Bode in Germany to confirm the observation, but it's no longer visible. The orbital calculations at the time are too primitive, so the object is lost. Gauss develops methods for finding orbits on the basis of 3 observations, purely to solve this problem. He applies it to Piazzi's data and produces a prediction of where the object should next appear. So von Zach, at the end of 1801, uses this prediction to relocate the object. Piazzi names the object, assuming it's a planet, Ceres. Its location at 2.77 astronomical units reinforces this numerical sequence of the distance of the planets. But of course, it's not big enough to be a planet, and we know it today as an asteroid. Herschel determined the size of Ceres to be 260 kilometers, a very crude estimate. The modern value is close to 1,000 kilometers. And you see here in a scale the distance or the difference in size between the Earth, the Moon, and Ceres. So it's much smaller than the Moon of any of the planets. It's called an asteroid, star-like in appearance but much smaller than a planet. Olbers then discovers another planet in similar orbit, which is called Pallas. And then Juno and Vesta are found, and eventually large number of asteroids are found, smaller and smaller through the 19th and 20th century. There are, of course, literally millions of rocks in that region of space. Only the largest could be found with the telescopes of the time. And so we see this as the discovery of the asteroid belt, large pieces of rock in a broad band between 2 and a bit and 3 and a bit astronomical units, with the rocks ranging mostly from 10 to 100 kilometers in diameter. Ceres is the largest. This is now known to be leftover material from the formation of the solar system. And here is our map of the inner solar system with the addition of the asteroid belt, the objects that were discovered during this period of time, an exciting time in astronomy. We also have the subject of celestial mechanics, the idea that the mathematics is now good enough, using Newton's law of gravity, to predict the motions of planets, comets, and asteroids, and to use this information and accurate timekeeping and more accurate telescopes to predict when they might be observed in the future. The mathematics of it is that you need 6 pieces of data plus a knowledge of the forces. You need 3 observations of their location in the sky, the 2 angles, right ascension and declination, and that data is transformed into 6 orbital elements. We see an example here in 2 different dates for Mars of the orbital elements. The orbital elements change over time due to gravitational influences of other planets and the shapes of planets. And so detailed calculations are needed at every point to predict the positions of planets in the future. Kepler's laws are really only approximations because of these imperfections in the data and the gravitational influences of objects on each other. But through this time, into the 18th century, we have a much more sophisticated form of astronomy that's able to track the motions of objects in the solar system. And that's the end of this topic.